Hello and welcome to today's webcast titled Modeling Fluid Flow in the Power Generation Industry, Challenges and Solutions. I'm Aaron Larson, Executive Editor of Power Magazine, and I'll be moderating today's program, during which we'll hear from Trey Walters, Professional Engineer and Principal R&D Engineering Software with DataCore Engineering Software Group, and Anna Kanlari, who has a PhD and is the product marketing leader for DataCore Engineering Software Group. To give a little more background on our two speakers, Trey Walters founded AFT, now DataCore Pipe Flow Modeling, in 1993. He holds a Bachelor of Science and Master of Science in Mechanical Engineering, both from the University of California, Santa Barbara, and is a registered professional engineer. He was the original developer of Fathom, Arrow, and Impulse, and has taught hundreds of training classes on DataCore's pipe flow modeling software products in 12 countries across every populated continent. He worked previously for General Dynamics in cryogenic rocket design and Babcock & Wilcox in steam and water equipment design. Anna Kanlari has a PhD in chemical engineering and is a technology and commercial leader with more than 12 years of experience who works at the intersection of engineering strategy and customer impact. With a background spanning petrochemicals, specialty chemicals, energy, and refinery operations, she focuses on making complex technical ideas clear, practical, and actionable for industry leaders. Her work centers on digital transformation, sustainability, and helping organizations unlock real value from advanced technologies. The presentation is expected to last about 45 minutes and will be followed by a Q&A session. Before we get started, I'll run through a few housekeeping items. In the webinar platform, you should see a chat area and a Q&A area. If you are experiencing any technical difficulty, you can ask for help using the chat function, and our production staff will assist you. To submit questions for our speaker, please enter those in the Q&A section rather than in the chat area. You can enter questions at any time during the presentation, and we'll answer as many as possible at the end of the program. Any that we don't get to during the live session will be answered via email after the webinar. Today's presentation will be archived on our server for up to a year, and future viewing will remain free of charge. You can use the same URL to reach the archive program as you did to reach the live program. PowerPoint slides will also be available from that URL. The certificate of completion for professional development hours will be sent via email to every registered participant who attends. And before we begin, I'd like to thank DataCore for underwriting today's program. The company's generosity allows everyone to attend the presentation at no cost. With that, I'll turn the program over to our speakers. Trey, I think you'll be taking it away first, right?
That is correct. So we'll jump in here. First slide. Okay. That's not going to work that way. There we go. All right. So what we're going to do is I'm going to start today, do this first slide, hand it back to Anna to tell you a little bit about DataCore and what we do with our engineering software group and some of the other product areas in the company. And then I'll come back in later and get into a little bit more of the technical stuff around the fluid flow. One of my favorite movies, and as Aaron introduced, my first job was in cryogenic rocket design. So and that leads to like one of my favorite movies being Apollo 13. And there is a scene in there with the engineer. And one of the nice things about this movie is they really got the way engineers communicate. They got that down really well. You could tell that they were really well coached. But John Aaron, who was responsible for the batteries and the power on the Apollo 13 mission lunar module, he has this line in the movie, and he says, "Power is everything." And in our modern society, that's true. Between power and materials, nothing happens that happens in our modern society today. And so the topic that we're going to talk about today, and probably all of you work in, I think we're aware, is this a very important topic. to have secure and safe power. And so with that, I'm going to pass this over to Erin. I'm sorry, to Anna, my colleague at DataCore, and let her tell you a little bit more about us.
Good morning, good afternoon, everyone. Thanks for joining. Before jumping into the presentation, I wanted to run 2 poll questions just to get a feeling of who has joined us today. So if you can see the first poll question. All right. Which power generation sector is most relevant to your work? So there are 4 options: fossil fuel, nuclear, combined cycle, or renewable or emerging technologies. So which one of these is related to you? Okay, great. So almost half of our audience come from the fossil fuel background. Oh no, it's changing. All right. Now we're getting more and more renewables. That's great. Okay. Okay, now if we move to the second question. So we wanted to understand your use cases for pipe flow modeling tools. So which one of the following best describes your primary use of fluid flow modeling software? Is it steady state design and sizing? Is it transient and surge analysis? Is it heat transfer and thermal balance? Or you're not currently using a flow modeling software? So it seems that most of you are using it for steady state design and sizing, and about 30% that who haven't been using the software. All right, so here's the agenda of the webinar today. I'll give a brief overview of DataCore, who we are, what we do, and also a quick overview of the power industry. After that, I hand it back to Trey, and he's going to talk over the products more in detail. But the majority of the webinar is focused around real-world case studies and in the power industry. So the way that our clients over the years have used our software and what was the result they got, what was the value that they got from this application. And then we will wrap up the presentation by some highlights. So DataCore is a company that started back in 1982 as enterprise resource planning software. After that, over the years, it has grown organically and inorganically. Through acquisitions, it has formed the engineering software group that both Trey and I work for now. So the first acquisition was in 2021 for the engineering software group with the acquisition of ChemStations. ChemCAD process simulation, for those of you who might be chemical engineers and familiar with that. And the second one is AFT, Applied Flow Technologies. That is the topic of the presentation today. We have a broad international presence. Aside from the offices that we have globally, we also have a broad network of our partners that we cater to customers in pretty much every region of the world. One thing that we are very proud of is our collaboration with universities and research institutions. We have over 125 universities that are using our software for training their engineering students. And that's something that is very important to us, to have a share in this training and getting them ready for their future career. I already mentioned about enterprise resource planning software, but there are also other range of products that DataCore offers, including CRM, including laboratory management, LIMS systems, supply chain, asset tracking, formulation, and labeling, manufacturing execution systems. But last and not the least, process and flow simulation. And the flow simulation, again, is the topic of our conversation today. So why is flow analysis software important to the power industry? So first and foremost is about efficient designs, to making sure that the designs are accurate, adaptable, and they cater to a wide range of operating conditions. And what do I mean by that? As the power industry is going through this transformation, they're going to be need of future power generation to be adaptable, to bring in renewables. At the same time, they with fossil-based and typical generation, at the same time as using storage. It's important for a power generation facility to be adaptable to the fuel size, perhaps, even if they're using fossil fuel. So there is a lot of flexibility that these facilities need to be successful going forward. The second item is about ROI, about existing facilities. A lot of these facilities are decades old now. So how we can make them more efficient, how we can help them save energy, how we can make them produce more electricity. If you think about that, a typical coal power plant is only 35% efficient. So that highlights the implication of trying to improve the efficiency of power generation. The second item is about reliability, minimizing downtime and repairs. For those of you who work in the industry are familiar with the huge costs associated with these kind of repairs. And the other thing is that with the number of projects that are in the pipeline, there is a huge almost competition to get access to the equipment, power generation equipment, especially like turbines, right? So it's not that they are immediately accessible. There might be a couple years to a few years wait times for these. So let's make sure that our equipment, existing equipment, are healthy and we are monitoring them. And finally, it's about safety and environment, ensuring resiliency and safety of the design, because incidents can have catastrophic consequences, right? And in these systems with fluid flowing all around the pipes, so there might be surges, there might be transient forces exerted on the piping system. There is water hammer, steam hammer, and many of the things that Trey is going to talk and cover during this presentation. So we have to make sure that our systems are resilient to respond to these unexpected changes. And finally, it's about minimizing emissions. Power generation industry is one of the primary contributors to the greenhouse gas emissions. So and any steps taken towards sustainability goals trying to minimize these emissions can be a success for the industry. I already mentioned about the power generation industry that we have been serving them for decades. The other industries that our fluid flow modeling software have been used are in energy and chemicals. There is also consumer industries and heavy industries. So in the next slide, you're going to see the wide range of customers that we have worked with in the past. They are owner-operators, there are EPC companies, there are government laboratory research, and there's also research organizations like NASA that they have been using our fluid flow modeling software over the years. These are some of the case studies. I just pulled them from our website, whether it has been helping to improve throughput of a chemical plant, whether it has been reducing power consumption or making sure the reliability of a cooling system in a data center or increasing efficiency. So these are just some highlights of the value that has been achieved or gained by our customers through using our software. Now let's take a quick look at the status of the power industry. So demand acceleration. Deloitte published an industry outlook for power and utilities in 2026, and they are projecting the power demand in the United States to grow by 26% by 2035. And the majority of it is going to come from the boom of data centers and their need for power, about 176 gigawatt of it. But there's also other players here. For example, on the decarbonization roadmaps, there is a need for electrification of heavy consumers of energy. So that's also going to account for about 25 gigawatt of power that is going to be needed by 2035. On the supply side of things, in 2025, they estimated about 93% of the new supply that came online came through renewables. But that is expected to change also, especially with the shift in government policies. And there's a lot more incentives and investments in power generation, either based on fossil fuels or based on nuclear. And these investments are going to change the landscape. And one important thing here is also power generation behind the meter that is catering to hyperscale data center users. So that's also another aspect of the demand that is going to be for the next decade, at least. On the infrastructure side of things, Lawrence Berkeley Lab had published some statistics that they estimated about 2,300 gigawatts of power can potentially be added to the grid. But there's a caveat. A lot of these projects are going to die down because they're never going to get permitted to actually get connected to the grid. There is going to be a transmission constraint, and there's going to be reliability issues. And as I mentioned in the previous slide, there is also going to be the behind-the-meter players that are not going to be counted actually toward the grid capacity. So with all of that, just as a summary, so what is the strategic imperative? Making sure that both the existing power generation facilities and the ones that projects are going to be designed are reliable, efficient, and safe. That's the imperative, what is needed for these projects. And our topic today is advanced flow modeling. So how flow modeling can contribute to that. So over the next slides, the rest of the presentation, Trey is going to go over examples of risk mitigation, transient risk mitigation, water hammer, steam hammer. He's going to go over optimization of power plants. How can flow modeling help with that? And he's going to give examples also of improving operational accuracy and improving ROI in the power generation facilities. So with this brief introduction, I hand it back over to Trey. Trey, thank you.
All right, thanks, Anna. So we're going to pivot now and talk about some of the case studies and a few technical papers that we have accumulated over the years. Power generation has been one of the biggest sectors of that we deal with here at the AFT and now DataCore that we've dealt with over the years, and we've been very successful there. What I understand from talking to a lot of you who work in the industry is that our software is considered by many to be like the leading standard software. It's the go-to software for people who need to look at fluid flow in their systems. And so that's something that we're very proud of. I'm going to talk about the 4 products today that Anna introduced. Fathom is our steady flow, essentially incompressible liquid modeling software. Aero is steady flow compressible. And then Impulse is water hammer, and Extreme is steam gas hammer and gas transient software. So those are transient oriented, and they help you do a number of things that are of interest in trying to make sure that your systems are efficient, safe, etc., and projects are completed in a timely manner. One of the things that we have a real strong point in, and I'll talk about at the very end, is calculating unbalanced forces in piping that is due to liquid or gas or steam transients and what happens in the piping on that. So as Aaron mentioned in the introduction, I was the original author of Fathom. Both Fathom and Aero were written in the basement of my house back in like the early 1990s when AFT was getting started. Impulse was partly written in my basement and then part by me, and then partly after we moved out into an office. So I consider those 3 sort of like my children. And then Extreme was one of my grandchild. And that was some other people led by one of our developers, senior developer, Scott Lang. That's been out in the market about 5 years. But Fathom and Arrow and Impulse are all over 30 years out in the market, commercially used for 30 years. Impulse was like first order was in the power industry. It was a power utility. And they actually, when they heard we were developing it, they sent us a purchase order before it was even completed because they needed a water hammer tool so badly. And so it's a well-known power utility in the United States. Okay, so some key features that we offer in our software. So drilling down a little bit more from what on Anna's introduction. So one of the things that we've always done from the beginning, and not everybody does, actually most other commercial solutions do not do this, is actually modeling coupled heat transfer in your system and doing a system thermal balance in addition to the flow and pressure balance. And so we've been doing that for 30 years. So it's one of the reasons the power industry likes us, because this is an important part of a lot of power generation systems. We also are, I believe, the only company really that offers a goal seeking control and multivariable. So you can do not just single variable, but multivariable goal seeking control. Fathom and Arrow do that. Surge transient type simulations, impulse and extreme, bulk transient simulations, that's in Fathom and Arrow with XTS. Imbalance transient forces, that's impulse. And then this one right here, Anna, should be extreme over here on the right. So impulse and extreme do imbalance transient forces. All of our products have a scenario manager that we've had in our software for about 25 years. And people who use that, I'll show you one example today that came from Kiewit and on a combined cycle facility they worked on that they use scenario manager. And most of engineers, the feedback is we are by far the most advanced to be able to manage your design cases all within a single file, interrelated by hierarchy. And then also all of our software has code compliance type features in it, notifies you when you're outside of codes and things of that nature. Okay, so these are the industries where we actually have case studies or technical papers, mostly case studies, okay? And so over on the right, I tried to break these down by just in application areas within the industries. And then the gray areas are ones that you just are not applicable for that particular industry. And so when you see a letter in here like F and I, that means that we have in the fossil industry, coal, oil, primary cooling or heating systems, we have at least one Fathom and at least one Impulse case study on that. And so, but our software gets used in all of these squares. We just don't happen to have case studies in all of them, but they get used in all of this, okay? The case studies I am going to talk about are listed here. So the first one I'm going to talk about is in the nuclear industry, which is a secondary cooling system, which can, in emergency cases, can become the primary cooling system for a nuclear reactor. It's a safety system. I'm going to talk about that. Then I'm going to talk about a combined heat and power system in Germany. I'm going to talk about a gas turbine supply system done with AFT Arrow. And then I'm going to talk about Impulse that was done on a combined cycle, but this was on the cooling water side, so the steam power generation side and the cooling water, condenser cooling water side for Impulse. And then I'm going to talk on two cases right here. We have a case study that's a natural gas supply transient in the fossil industry, natural gas. And then there's another one. This is really a technical paper that I wrote. There's actually like three, but one primary one here. And I'll talk about that if we have time. So that one paper hits kind of all the steam, high and low pressure steam systems that you're going to see like in coal, oil, fossil, or the on combined cycle on the steam side, and then just traditional nuclear as well. Okay, so let's dig in here. There's other things than that in that matrix that we do, and we have customers using our software. Like we have customers using our software in geothermal. We have customers in this SMR area. We have customers that have evaluated biofuel heat sources. We have customers doing hydropower with our software. Pump as turbine has been an emerging thing that people do for usually low power availability type systems. But and then we have customers that are actually manufacturers of steam turbines, gas turbines, cooling towers that use our software for the internals of their equipment. And so we have quite a number of customers who make steam turbines, who make gas turbines, and use our software on the piping inside those pieces of equipment. Some of them are the rotating part for like blade cooling and things like that. So we have a number of customers do that. And then we get used in energy storage as well. A couple ones that involve fluid flow or pumped hydro get used in that. And then I'm going to talk about a case study today that gets involved with thermal energy storage in Germany. Okay, let's talk. So I got 2 case studies on Fathom, and we'll move along here. First one is a hydraulic model calibration of a nuclear plant service water system. The second one is a combined heat and power plant central heating cycle. Okay, this particular example was one that we published about 10 years ago. It was done by Duke Energy in North Carolina. So those of you outside the United States, North Carolina is over in the East Coast, show you kind of around there. The first unit has two reactors there, and the first unit opened in 1981, the second one 1984. The project goal was to develop and calibrate a hydraulic model of the nuclear service water system B train at the McGuire Nuclear Station. These systems were backup cooling systems for the Unit 1 and 2 reactors. And so they weren't the primary cooling system, but if the primary cooling system had issues, then they would draw on this RN service water system to provide cooling water on the reactors. So these were considered safety systems. And those of you in the nuclear industry know that this whole project had to be done with nuclear certified safety and a nuclear certified type of a project. Some of the systems that were being modeled, there was modifications that were being done at the Duke Energy plant, like a lot of the plants, probably around the world, but certainly in North America, as a result of the tsunami in Japan and the Fukushima accident at the nuclear power plant in Japan. And so there were some modifications made as a result of that. And they wanted to evaluate those in their cooling water system before they actually made the changes. They wanted to see what was going to happen. Okay. So, basically they had 4 different systems here. They had 2 units and an A and B train to 2 units. So we were focused on the B train system, and they pulled water out of a lake. So the power plant at Duke McGuire is right next to Lake Norman. But if there was an issue with the lake, then they had a pond that they could pull water from. But primarily they pulled water to Lake Norman. I'll show you in a moment what that looked like as far as what it did to their pipes. And then they had the pumps came in, and they had a whole bunch of heat exchangers. I'll show you a little bit later, but they call these the major heat exchanger loads. This is the 1B, the B train going to the Unit 1, and then another independent one going to Unit 2, and then they could cross over if they needed to. And then they had a bunch of minor load heat exchangers. And then they had these CA systems, and these were the ones that made for the main backup to the primary cooling systems for the reactors. So because they were pulling water out of Lake Norman, these are actual pipes that they pulled out of their operations and took photos of. And so what they would do from time to time when they were in a downtime on the plant is they would go in and they would clean these pipe outs, and they'd clean out these tubercles that were inside. And one of the things they wanted to get out of this project is understand where were the worst ones. So if they only had so much time to clean these out with like some sort of a laser type cleaning thing that they did, they want to know which ones to focus on. Okay. So you can see obviously there was fouling, and which would affect the diameter of flow, which increased the velocity. And I don't know what you do with the roughness on here, but we were able to do some calibration to try to estimate what these were by matching against data. Okay. So there's modification of the internal diameter of the pipes because of scaling and modification of the roughness. Duke Energy had 3 different data sets of different operational configurations. So it wasn't just measurements from one operation. They had 3 different operations of this particular piping system. So we were trying to work with them to calibrate so that they would get scaling and roughness that would match not just one data set, but match 3. So that was quite the challenge. There were 15 to 20 flow and pressure measurements taken in each data set, and they used our Fathom goal seek and control module, which is multivariable. So we're actually talking about 15 to 20 goals that we're trying to search for, and it's well suited for multivariable goal seeking such as this project. So previously, Duke Energy did this task manually, which they said was quite time intensive. This is a Fathom model of the Unit 2 B train systems, and don't want to go through all this, but just to point out that These were the red ones were the major load heat exchangers, the biggest ones that they had to deliver to. They weren't controlled by control valves. It was all basically kind of controlled by friction is how they delivered. So they wanted to make sure they got that sufficiently. And then the blue ones were other heat exchangers they called minor load heat exchangers. Okay, calibration results overall satisfactory. And I also want to mention that the cases that we're talking about today should all be in the handouts. And you should be able to go. So I'm not going to be able to talk about them all as much detail. I love talking about this stuff, but as much detail as I would like. So if you're interested in any one of these or all of them, whatever, you should be able to read the handouts. So we have write-ups on all of these, okay? So they had a 1B system, partial calibration, 2B system, complete calibration is what we worked on. Satisfactory results. They really wanted to make sure their major heat exchangers were satisfactory, and the minor load flow paths were pretty good, but not 100%. It was a complex thing. But here's some of the results they got on the Unit 1B train. So we got flow balanced in the model by doing again changing roughnesses and scaling and the ID on the pipe. Got it balanced within 2.1% in the model, and pressure within 1.2 psi. And then in the Unit 2B train, flow within 2.3%, pressure within 1.4 psi. Okay, let's move on to another case study. This was done, as the Duke Energy one was done about 10 years ago. This was done just a couple years ago. It's a company in Germany called Enka. And this is and forgive my German here, Drahtenau combined heat and power plant. It's in Hamburg, Germany. It includes combined cycle power generation. It's a very complex integrated system. I'll show you here in a moment. It was designed, and they were doing the modeling using Fathom back like in 2022, 2023. What we understand looking online is over here, and if your European map over here in Germany, and it came fully online last year is what we see online. We go on their website. Fathom was used to design the combined power and heat cycle. Challenge, a new state-of-the-art facility to produce 180 megawatts of electrical capacity and an additional 260 megawatts of district heating utilizing multiple sources, including waste heat from local industrial processes, a natural gas power plant that was built. Engineers needed to design the thermal loop, hydraulics, and size equipment pumps and the piping system. They used a scenario manager in Fathom to model heating storage, extraction cycles, with and without the heating condenser. Other modes, they had to look at summer operation, they had to look at winter operation, what the industrial heat supply is, whether the heating condenser supply, steam turbine trips were simulated, minimum, maximum flow pump trips. So they had a whole bunch. And if I remember, there was like 17, and we might say that in here. I think there's about 17 different scenarios. This is a picture on the right of the facility. This is the thermal energy storage tank that they did to store thermal energy that they could then distribute and use in the winter. So they leveraged Fathom different heat cycles with the heat pumps, heat recovery systems, gas turbines, HRSGs, and they modeled that, sized the pumps, lines, control valves, determined complexity of the design was simplified using our scenario analysis tool in Fathom, and Fathom guaranteed accurate design and future reliable operation of the plant. Some of the things they did in here, this was a very wide-ranging case, the combined cycle generation, different operations in there for the gas heat, for gas turbines, cooling, for steam turbine condenser, et cetera. They were integrated with the local industrial waste heat coming from steel production, a sewage plant, incinerator. They stirred up to 50,000 cubic meters of energy and 13 million gallons that they could use in winter. They had like 17 heat exchangers, and again, they had like 17 operating scenarios. So if you want to read about that, again, it's on our website, and I think also in the handouts. Well, this is what the model looked like. It's a busy model, but it handled all the different things that they were trying to do in here. I'll point out a few things right here. This was they captured the waste heat in here, heat extraction portion of the plant, where waste heat from industrial suppliers and heat from the plant's steam power cycle are captured. And so this is this portion of the model here. You can see a blow up over here on the right. And then also a secondary, they actually took heat that was generated from this, and they used it for district heating for local residential in the area around Hamburg here. So that was kind of an interesting thing, very integrated type of a system. And so this down here is secondary water system, which a group of 5 heat exchangers transfers heat into the district heating system. So that was going in, and you can see around here where the 5 heat exchangers were transferring that heat that would go out into district heating. Let's talk about compressible flow. We're going to talk about something called EGT spread. I think I understand it's a pretty well-known concept for those who deal with gas turbines. There's a company called Fern Engineering. This is a long time ago. One of the early customers was Arrow about 30 years ago. And they are in the United States, up in Massachusetts, up in the upper northeast of the United States. And there are critical flow sonically choked orifices and ventures. They were trying to model a Rolls-Royce Avon gas turbine at this time for power generation. This is now part of Siemens. The challenge is the gas turbine system EGT spread, exhaust gas temperature spread, could impact lifespan operation of turbine components. EGT spread is caused by variations in flow and temperature of supplied fuel. So what you really want to get, again, not expert on this, but from talking to people who are, you want to get your delivery of your gas into your gas turbine as it goes into the injection points around the gas turbine. You want that to be thermally and fluid and flow balanced. And if it's not thermal and flow balanced around the periphery, it can cause some reliability issues with the turbine, the rotor, et cetera. And so you want to minimize that. And that's what they were trying to do. Engineers needed to model multiple sonic choking points in parallel paths to accurately predict flow and temperature distribution at multiple fuel discharge points. They chose Arrow to model this turbine system due to the ability to model critical sonic flow orifices and ventures and the ability to model a large number of elements. Additionally, what they did is they benchmarked. And so they did some measurements on Arrow's sonic choking prediction against test data. I'll show you that. They did numerous runs of the model, and baseline was run reflecting the nominal configurations. Okay. Results, they modeled the system estimated flow and pressure variation around the injection points due to expected tolerance variation, which then informed the EGT spread. Okay. So first we'll start with the model of the turbine. So the fuel nozzles are over here on the left. Before the fuel nozzles, there were these orifices that all had sonic choking. So we had 8 sonic choking points in parallel. There was other places in here you could get sonic choking, but in this case they didn't. It was just these, but it was possible based on the configuration it had. Okay, fuel supply was over here on the right. Before they built out this model, what they said is, before we're going to do this and trust results, we want to test something. So they literally went out into their out back, and they built a little test facility with air, and they took a low pressure air system right here. This is like, I don't know, 4 or 5 bars. And they went through an orifice and they measured what was going on. And so over here, they measured the, you can see the flow that they measured in pounds a second and kilograms a second. They measured the pressure at the orifice right here. And then they, and this is what Arrow predicted over here. So you can see, you know, if we stick with pounds a second, it was within like, gosh, about 2% on flow, and pressure was off by about 0.3 psi. So they were very happy with that. So after they did that test, that benchmark, then they went ahead and built out the full model over here on the left, and they completed the project. Let's talk about impulse. We're going to talk here about a pump trip transient evaluation. Actually, they had pump trip and startup in a combined cycle power plant. This particular power plant was opened about 10 years ago. It's in Woodbridge, New Jersey, and it's called the Woodbridge Energy Center. Again, it's all in the northeast over here, not too far from New York. Those of you international. It's a 725 megawatt combined cycle power plant. The engineering was done. It actually opened in 2016. Here's a picture of it. And so a few years before that, one of our customers at Kiewit did some modeling on it. And right now we're going to focus on what they did on the condenser cooling water system. Okay. So, they wanted to improve reliability and safety of the combined cycle power plant is what they were able to do. The challenge, it's a combined cycle natural power plant. As I mentioned before, 725 megawatts. They had a water circulation loop, was complex, and included 2 vertical turbine pumps with 158,000 GPM, 36,000 cubic meters an hour. Total flow, 14 cooling towers. The circulating water system needed to be evaluated against pump trip and startup scenarios to ensure reliability and safety during surge and transient events. Solution is they first built a Fathom model, a steady state. And then what they were able to do is they were to take that entire Fathom model and port it completely into Impulse with all the data in there. And then they had to put in the transient things in Impulse. The model was color coded to improve readability. And then they explored 46 scenarios for pump trips, all in a single model file. They did profile graphs of the system, made it simple to understand result-specific components. This is let me see. So results were study ensured no major transient events would occur, and all equipment and piping our equipment and piping are sized and rated to withstand any potential surge events. This is a quote from Dalton Civils, who was the engineer who did this. What he said was, being able to roll over the model into impulse from Fathom and as necessary is a great time saver. Then setting up all the different scenarios, being able to take the results and produce graphs to transit system all within one program saves time and effort. Show you real quick the model. So over here, these are there were two condensers right here. These are the air valves around the condensers. They also had a parallel path for a condenser cooling water system heat exchanger. These are the two pumps, the vertical turbine pumps. And then these were the 14 cooling towers. These are all of the scenarios. This is a screenshot out of Impulse of all the different scenarios that they had set up and run to look at different type of cases in here. And you can see in here, they're looking at 2-pump start and 2-pump trip and one pump tripping and et cetera. All different cases you need to look at to make sure you got a safe system. Okay, let's talk about extreme. So we have two things to talk about. One's a case study that we just got last year, very interesting, on a gas turbine, natural gas supply to gas turbines, a system reliability done with extreme. We'll talk about that. The second one is transient forces and pipes and predicting that during steam turbine shutdown. Okay, I think we're probably only going to have time for the first one. The second one, I'll summarize. There should be a full explanation in some of our downloads, but if I have time, I'll go through this. But I might have to go real quickly just in the interest of time. Okay, so the facility is in County Westmeath in Ireland, called the Castlelost Flexible Peaking Plant. New plant construction was completed in 2025. Their website didn't say that they'd gone operational yet, so it sounds like they might have just completed construction late in the year. It wasn't quite clear whether it was up and going, but I suspect that if it hasn't, it's going to be doing soon here in 2026. So again, your Europe map and Ireland, I thought a lot of us know where that is out there. The island, and this is like a photo of the plant. What you can see in here is there are 5 gas turbines, 5 units in here, and that's what they did on the initial design of this. This is a total greenfield project. And so there are 5 turbines, and then we'll show in a moment, they had to also look at future capability where they would add 2 more gas turbines onto this. Extreme helped them reduce operational risk, eliminated turbine shutdown, improved compliance with the OEM, which was a Siemens, actually. You got a Siemens screenshot over here. Siemens supplied the gas turbines, and they had compliance with OEM and regulatory requirements. Excuse me. The challenge was to build a new 275 megawatt open cycle gas turbine plant, but it has can have fast load swings, transient gas pressure fluctuations. The gas regulator response could lag up to 5 seconds, which can cause pressure dips, spikes and dips, turbine alarm shutdowns, gas supply interruption potential, G&I slam shut activation. And just what they want to do is maintain stable turbine inlet pressure. It's critical. And so if you have upsets to your system, or especially like if one of the turbines is going down or starting up, are they impacting the other 4 turbines that are in operation? And they're trying to keep things within an operational limit here so they can maintain operation. And so they used Extreme to evaluate those different cases. And so I'll tell you how that worked out for them. Again, they used Extreme, high fidelity transient analysis, full system. Extreme uses method of characteristics. Those of you who are into geeky computational things like me. The full system was modeled from the G&I regulator to the Siemens gas turbines, 4 scenarios, tested per configuration with different load and trip scenarios. Model was incorporated into regulator response, buffer volumes, alarms, turbine limits, and worst case boundaries. Okay. And results, they concluded the system met all operational, regulatory, and OEM requirements for both configurations, both being the 5 and the 7 potential 7 turbines down the road. No event exceeded the gas pipeline slam shut limit. Ramp up pressure stayed within the 29 bar low pressure limit, and all transient fluctuations remained within the 1.5 bar allowable limits. I'll show you what that model looked like. So the as-built, which they built and finished last year, was this configuration is what the photo, I think we don't, we showed you the photo earlier. This is the 5 turbine setup over here, okay? And then what they wanted to do is they wanted to allow for 7 turbines to add 2 more on later, and they wanted to make sure what they were doing right now would accommodate 2 more turbines later. That was part of the design, and I'm not going to read all these to you, but these are just some of the key results in here. That they had to have, different pressures and volumes that they wanted to meet. Overall findings, all scenarios met. This GNI, I think that's the local gas utility there in Ireland. Can't remember the name. The Irish gas utility, and the Siemens limits. They had no risks of trips, alarms, or supply interruption for the 5 and 7 turbine thing. So they were happy with that. They could go forward confidently with construction. Okay, I got a few minutes here to talk about this final one. This is not a case study. It's an actual technical paper that I wrote myself using Extreme. And it's one of the interesting things we came out. Extreme is a very unique product, and there's not really anything else like it on the market. We have a case right now, one of our customers using Extreme. This is interesting. And I'm not sure what the model is of, but they had a CFD model of their steam piping system and steam transients, okay? And they had run that, and literally their CFD model took 6 months, push the button to run, 6 months to get results. And so they had acquired Extreme to model that, to do that faster. And I'm not sure, CFD is not that it's poor, it's not the right tool for everything. And so they were very happy with Extreme could model that same system in 4 days. 4 days sounds like a long time to get results, but they were comparing 4 days to 6 months. And Extreme's like a very unique tool. You can do some of it with CFDs. The CFD is going to take longer to run. It's not really suited for it. And Extreme is vertically associated with transients, gas and steam transients in piping systems. Okay, so pipe forces in steam piping. Okay, common practice methods for estimating piping loads due to steam hammer have been used since the 1980s. They've been used to basically model lots of power plants, probably almost all the nuclear plants we have out there. Recent studies indicated that these methods were not conservative. I'll show you what that looks like. Extreme confirmed and clarified these recent studies and provided the detailed analysis results needed to explain the deficiencies in common practice. This should alarm everybody who deals with high pressure, high flow steam applications and are looking at pipe supports. We looked at cases that you might get piping loads that were underestimated by a factor of 2 or 3. And I'll show you some of that. And that should make a lot of people who've designed piping systems and pipe supports for steam lines very nervous. And if it was me, I'd go back and maybe re-look at those with a new tool, but that is what's going on, okay? So why are transient forces important? Fluid transients, such as water hammer, surge, steam hammer, etc., they cause transient forces. These transient forces can be very large, like 10,000 pounds, 50 kilonewtons. They can be higher. It's common. Resulting stresses can cause sudden failure on piping or fatigue failure. The failure from these forces is more often on the supports and not, it could potentially cause piping failure, but they're more likely to cause support failures, and that can be bad as well, okay? Designing a safe system requires accurate transient fluid forces. And so what that means is, like safe systems, you have to have stress analysis. You need a fluid transient analysis, which Impulse can do for liquids and Extreme for gases and steam. And then you need those transient fluid forces that feed back into this dynamic stress analysis to make sure the pipe supports are properly designed. How do fluid transients cause transient forces? So I'm going to talk about this a little bit more in the terms of like a liquid wave and not a gas wave. Same principle applies. But in steady state operation, I'm not going to go through all of this. I'm going to just summarize it real quickly. Then I'll show you an animation what it looks like. You have operation going on, and it's all in steady state, and it's all in mechanical balance. Okay, there's nothing should be moving in this. It should be just if it's steady state, all of the forces sum to 0. So there's no, sum of all forces are 0. Nothing is really moving as far as the piping concerned. But the fluid is going from left to right. Okay, and then as it goes, there's this leg that it goes through. We're going to call it leg 1, 2, where the fluid has to go through to get from point A to point B. Okay. Now over here on the right, there's a transient. In the case of like we're going to talk about here in a moment, in a steam line, a steam turbine, you have an emergency shutdown of the steam turbine, and and the shutdown valve suddenly stops the steam flow, and it progresses back. And at a certain point in time, that acoustic wave traveling at a wave speed A is right here. And if you look over on the right, you can see the force goes up really quickly up to some level. And the question is, how high is that force and how long does it last? And there's conventional methods for that, and they really don't get either one quite right. Unconservative methods, okay? Eventually the wave goes all the way down to the left and goes out. We're back in equilibrium again. It's under high pressure now, but it's under a steady state high pressure, and the forces go back down here to zero, okay? I'll show you what this looks like in terms of an animation. Okay, so we'll just say there's like water flowing out to the right, okay? We close the valve, and as you see, as the pressure goes through, it makes this section of pipe with the bends in it move. And that movement has to be constrained. If you don't constrain it with supports, it has to be supported. And if not, you're gonna get movement like that. And eventually, you're gonna get some fatigue cracking even on the joints in the pipe, and that could be bad. So you wanna be able to predict that. And so I'm going to summarize here real quickly, including all contributors to transient forces. So one of the problems with the traditional methods is that if you do a force balance on here, this is just basically Newton's second law of motion. And if you do this on the fluid inside of here and how it's interacting with the pipe structure, this is Newton's second law. This is F equals ma, okay, applied to this right here. The methods that have been traditionally used since the 1980s don't use, these are all of the forces that you have to account for. They don't account for all of them. They only account for some of them. And that's the problem. And so when you get to the tool like extreme or impulse, you can account for all this and get an accurate assessment of your forces, okay? This is a particular example that came from a paper done by some engineers at Sargent and Lundy on the nuclear industry. It's 1,000 PSI, 7,000 kilopascal steam supply. Piping is about 2,000 feet long, 600 meters, etc. And the steam turbine stop valve is down here, closes. And so if you look and you go down from the turbine stop valve, these different green areas are where we predicted the forces. This is the force prediction that comes out of doing a comprehensive calculation of this using extreme. This was the forces predicted by the traditional Goodling method. And you can see for this first leg right here, Goodling was not too bad. It's not too bad either, but it's unconservative for leg 4, which is right there. But as you go further and further down towards the steam supply, it gets worse and worse. And so since the 1980s, people have been using this red line to predict these because they didn't understand some of these complex mechanics that we're talking about here. So extreme can handle that, okay? And so you can see, like, get all the way out here to leg 19 and leg 16, these two, it was like the actual forces are 3 times higher than Goodling. And so if you used Goodling, you're under-predicted by a huge amount, okay? Conclusions. DataCore flow software has been heavily used in the power industry for 30 plus years. DataCore's family of software products offer the broadest range of products for power generation. We have 4 products and numerous add-on modules, many powerful capabilities only available that you find in our products. There's nothing else really commercially available like Extreme. And other things too that we do that we're only ones who really do certain things to help people in the industry. DataCore has over 20 case studies. I think it's 23 now. Case studies and tech papers for power generation applications which show the amazing breadth of our software in the industry. Not going to go over all this, but if you get the PDF, we have links. You can click on these links and find all the different case studies and tech papers we have, go through in these different industries, okay? And with that, I'll stop and pause for questions. And I think, Aaron, you want to jump back in.
Yeah, thank you so much. That was really interesting and a lot of information. So I want to remind people that there are handouts in the handouts tab that you can go and get further details on some of these things that Trey mentioned and really get a better understanding of it all. Again, thanks. And we have had a number of questions come in during the course of the program. We'll try to get to as many as we can in the time that remains. Again, I want to remind people, if we don't get to your question, we will answer via email after the program. So you will get an answer to your question. But the first one here says, does your software also do calcs for slurry fluids and other complex fluids such as carbamate? If you do, what is the calculation methods or international standards you use?
Yeah, so the answer to that is yes. We have an add-on module for our Fathom and Impulse software. called the SSL, settling slurry module. So we could do non-settling, non-Newtonian, non-settling, and non-Newtonian settling slurry models. The settling slurry models that we use are, there's a model that comes from GIW Pumps, which is now part of KSB. I'm not sure it technically has a name. And then there's a newer, they call it a 4-layer model. And we have that in our software. We use that for doing pressure drop in slurry type systems. So I think the answer to that is yes across the board.
All right, very good. How does your software handle / calculate sizing for supercritical CO2 fluids?
Yeah, so we have a lot of applications we've had at supercritical as long, and we can do we have different libraries that we can get properties from. Probably the most accurate we'd have along CO2, and users can also create their own thermophysical library. So if there's something you don't like that what we offer in our software for doing thermophysical properties, you can add in your own if you prefer. For CO2, so we've had a lot of supercritical applications in general, and also for CO2. If it's behaving as a compressible gas in the supercritical range, then you're going to treat that and it follows, and that typically that's going to follow the normal gas laws, and we can handle that with our Aero and Extreme software. So the answer would be is yeah, we can do that.
All right. The next question is about Fathom, and can Fathom and/or Aero now analyze combined steam, power, and water balances of complex steam / condensate / boiler feed water systems?
I think what that question is getting at is, can they do a single model to handle all of it in a single model? And we are getting very close to that. So it can be done right now, but we need to have separate Fathom and Aero models to do that. We just released, I think it was last summer, is we have an API, so we can run with some scripting, and we can show you how to do it. You can run your Fathom model on your water side and like your steam side with Aero, and they will pass information between each other and run one, run the other. So that is where we're at right now. So we can do that in a way we couldn't do it before. And we're constantly trying to improve our API. We have some more improvements coming out over the next year or two, but we have some capability right now that you can in fact do that.
Okay. And going back to some of the slides that you presented, it says, which forces are they not accounting for on slides 46 and 40 through 48 that you are accounting for in your calculations?
Okay. What most people do in the Goodling method does is it takes the pressure force at the beginning of, we're just going to talk about the pipe run going across here, that particular one. This applies to every place between elbows, okay, or any place that you want to go between supports, okay? But they take the pressure force here, P times A, then they take the pressure force here, P times A, and then transient over time. So it's the transient pressure on the left, transient pressure on the right. They subtract the two. P1A1 minus P2A2. We take into account all of these other ones. Now, this tricky thing about it is often doing that simple method is often pretty good, okay? But sometimes, depending on how you're set up, it can be very, very bad. You can get very incorrect results. So one of my colleagues and I, Scott Lang, we wrote a couple of papers for ASME. They are on our website, and that explains all of this in detail. You're welcome to kind of go dig into all of that if you'd like. But we do these are all the forces that come out of Isaac Newton and the momentum terms, and we account for all of them. And so the ones that are ignored by conventional methods, they ignore momentum change across components like a valve. They ignore friction and friction force in here, pressure forces across valves right here, and momentum at the end. They ignore that, and they only do pressure. Only pressure at the beginning and end is the typical approach since the 80s.
All right, very good. Then talking about, and I'll probably mispronounce the name as well, but Dradenau CHP plant in Hamburg involves 17 heat exchangers and 17 operating scenarios. That's amazing. Can you give us a sense of how long it would have taken to model that system without the scenario manager, and what could go wrong without that kind of a tool?
Yeah, so they had all the different scenarios, and what a lot of software products do, the best they can do is they have like 17 scenarios. They have 17 different model files. What can go wrong is that if there's an update to your system design, you have to go change that in all 17 files. and things don't get applied. And if you miss one of those, then that's where things can really break down. You don't have data that is consistent between your scenarios just because of the complexity of all that. How long is it going to take? I don't know. That was one of the most complex things I've ever seen done with our software. It was very impressive. If you have all the data in front of you, this has got to be this has got to be a 1 month or 2 month project, for an engineer. You can also split this up among different engineers, combine things. So I'm not sure exactly how they did it at Enca Engineering, but that's quite a project. But trying to do it without having a scenario manager to manage it, there's a lot of things that could go wrong with that. And so,
All right. Well, we're coming up on the top of the hour, so I want to respect everyone's time, but this has been fascinating, and really appreciate you guys taking the time to go through it all. Is there any last words that you want to leave the audience with before we wrap up?
I guess I'll bite. So we have been real successful across the whole world at just tackling all these different systems. There's just a huge range of fluid systems that go on in different types of facilities. And we got a really broad range of case studies that show you our software has been used. A whole bunch of things that we can't show you because the customers haven't told us exactly. We're not at liberty to tell you. But power industry is one of our bread and butter. And as Anna said up at the beginning, there's a lot of growth happening and coming. And we would love to have you guys, if you're not already talking to us, to talk to us and let us help you make sure you're successful in those projects. So thanks, Aaron.
All right. Anna, any last words?
I think Trey put it great. I just wanted to thank the audience again for their time and joining us today.
All right. And I want to thank DataCore for underwriting today's event, and thank all of the attendees also for being here and being part of this interesting presentation. So thank you all, and have a great rest of your day.
Thanks, everyone. Thanks, Aaron.